This is a continuation of the 6.2 notes. This is just a diagram and some things that we're going to discuss, and I'll do one example. The rest of the examples we'll pick up on Monday in class together. The problem we did on part 1 of this 6.2 video was that we looked at some acute angles, and in one of them specifically, we were talking about it being in quadrant 1. The problem is that many application problems that you're going to see do not always have acute angles as the root of what you're doing. So we need to extend our definition of our trigonometric functions, and we can do this by thinking about placing the angle in standard position, remember, which means centered at the origin, and our angle can then rotate as many degrees as we need, or as many radians as we need, because we can think about going around in a circle as many times as we have to. So there's a picture here. It says if your angle is acute, then this is the situation. Now, before, we just called this opposite, adjacent, and hypotenuse, and that was how we defined our trig values. But eventually, we're going to be talking about how if you have an angle, you can pick a point out on the terminal side. Remember, this is the terminating side of the angle, and this is the initial side. So if you picked a point here, you could then draw a triangle based on that point. And that triangle would be a right triangle. Notice that the legs of the triangle have to do with the actual values of the ordered pair. That's going to be crucial because that's why this length is x and this length is y. Because this is, if you were plotting a point, you'd go right or left and then up or down. So these actual values here relate to what is the opposite value and the adjacent value. The value over here, the hypotenuse, now this is called r. That's because when we get to the circle, the unit circle, that's going to be the radius of our circle. But right now, we're just talking about it's the distance from the origin to the actual point. So our r is our hypotenuse. So that means sine theta is opposite over hypotenuse. So it is now, can be represented by whatever value the y value of that point is over the hypotenuse or the radius. And then cosine theta is adjacent over hypotenuse still. It hasn't changed. But the adjacent is this x value of this triangle. It's actually the x value of that ordered pair. And then we place that over hypotenuse, which is the radius. And then lastly, because of course if you have these, you can get the reciprocals, the tangent is opposite over adjacent. So the tangent completely is dependent on not this radius at all, just the y and the x values. So y over x. So that's kind of interesting. It's a different way of defining it, and especially when we get to something called the unit circle, where we let r equal 1, you'll notice some interesting things. Sine will just be y, cosine will just be x. So these ordered pairs actually will relate to sine and cosine. And that's really interesting in and of itself, and that's kind of why the unit circle is so amazing. And then tangent is still going to be a ratio of those two values. So for now, this is just using the same idea of drawing a triangle, but calling the actual lengths what they are in reference to the points. So we've defined the trig values a couple different ways, but this one actually will be very useful for coordinate systems. And just so you note that the distance between the origin and the point that we drew is r for the radius, and that is the square root of x squared plus y squared because this is Pythagorean theorem. It's just related to the triangle. So then notice here the same definitions I wrote up above, and then all of our trig definitions will be defined as follows. The only problem is that anytime something other than r will show up in the denominator, it is possible in certain places in the coordinate system, mainly at like 90 degrees, 180, 270, and 360. You get things that are either a y-intercept or an x-intercept as your point. When that happens, you could possibly have a 0 in your denominator. So notice the ones that you worry about with domain, is whether or not the y or x is equal to 0 or not. So we cannot have those, otherwise that function would be undefined there. And that leads into this discussion right here. Because sine and cosine, no matter what, always have the radius in the denominator, that's that hypotenuse. The hypotenuse is never 0. Because if you have your coordinate system, and here's what I mean by that. Say your, initial say your initial point P is 0, 1, and your origin is 0, 0. Now, this definitely has a radius of 1, but the problem is anytime you wanted to put x in your denominator for one of the other functions, the x would be a 0. So that means that that function would not be defined there. And the 1 would be okay because y is 1 there. So in fact, in this case, when you are looking at your p being 0, 1, sine is defined, cosine is defined, tangent is not defined. So tangent is not defined at 90 degrees, so which is pi over 2. And then cosecant is fine, but secant is not fine because it has the x in the denominator. And remember, the x is our p points x value, so that's a 0. And cotangent is fine because the y is in the denominator. So you can essentially look at 90 degrees, 180, 270, and 360. Those are the trouble errors, those quadrantal angles essentially. And you'll see that certain things pop up. So here's the general rules. Sine and cosine are okay for every angle theta. Tangent and secant, notice because both of them had x in their denominator, they do not work at anything that is pi over 2 plus 180. Essentially, the big ones, if you go just one rotation around, are 90 and 270 degrees. So you can't define tangent or secant at those degree values. And you can check that on your calculator. Cotangent and cosecant would be when you have a 0 for your y value. So that's when you're on the x-axis. So that would be at pi, of course, which is 180, and then 360, which would be the next time you would also be on the x-axis. So you could go around and do that multiple times and keep adding, but if you're just talking about one revolution around the circle, those are going to be the angles. So this continues on, the pattern for both of these. You just keep adding 180, and every time you add 180, you get another group of degrees that don't work for tangent and secant, and for cotangent and cosecant. And then let me explain this last little piece right here, and then I'm going to do one example and then leave the rest, like I said, for class. This says for any point P in the coordinate system, x in the absolute value is less than or equal to the radius. Now what that means is you're talking about a triangle here. If you have a right triangle, of course, r is the biggest side because r is the hypotenuse. So yes, no matter what, if x is positive or negative, the absolute value of that, because we don't really want to talk about negative definition yet, is it's going to be smaller than the hypotenuse. And y is also a leg, so it's going to be smaller than the hypotenuse. But if you all of a sudden put x over r, you're going to have something that is small on top and large on the bottom. So again, that's a proper fraction. Proper fractions are less than 1. Y is smaller than r, and so this is a proper fraction. So you're getting that y divided by r is less than or equal to 1. So now what they did was, after you figured this out, you can replace this, that y over r, remember, is our sine theta, and x over r is our cosine theta. So now we know that sine theta in absolute value has to be between pretty much -1 and 1, because that's what they mean by the absolute value. Because -1 and 1 would both equal 1. So anything between -1 and 1 is where sine theta is. Cosine theta is the same. Because these are the reciprocals, notice that if something is less than 1 originally, like 3/4, if you flip it, it's now greater than 1. So that's why these two, I think of them as their partners, the inverses, the reciprocals. those are now greater than or equal to 1. So that actually tells you a lot about these functions, and we've never even graphed a trig function yet, but we already kind of know some behaviors that they're going to have about what kind of values will pop out. And then the last example that I wanted to do on this video is example 6. And it is if you have an angle theta in standard position and its terminal side is in quadrant 3, so that's this, the terminal side is on the line y equals 3x. Now, I didn't just make this point up. The way I figured out that point, I could have picked any point. Because this is in quadrant 3, I picked an x value that's in quadrant 3, plugged it in, so y equals 3 times negative 1, and that's how I got the point. Okay, so that point was not just made up, that's what it is. Find the values of the trig functions of theta. Now I'm going to actually redraw this because anytime I do trig functions, I like to think of triangles. Triangles are a lot more helpful. So if you think about this, don't worry about the rest of that line. If you drew a triangle from that point, so say this was my point negative 1, negative 3. I've over-exaggerated where negative 1 is. There's negative 3. So realize that the x value here, this side of this triangle, is negative 1. The y value is negative 3. We could find the hypotenuse by doing a squared plus b squared equals r squared, since we're going to call this r now. So this is like x, y, and r. So that is 1 plus 9. That would be 10. And if you take the square root, you get that it's the square root of 10. Now, you would question whether or not you make this positive or negative. R is not negative, ever, because R is related to the distance between 2 points, the origin and the point that you've drawn. So the only time you get negatives is either for the x's or the y's, and that just depends on what quadrant you're in. So if I wanted to write my trig functions here, y over r, so we already know our values. X is negative 1, y is negative 3, and r is square root of 10. So this would be negative 3 over the square root of 10. Cosine of theta is x over r, so that is negative 1. Remember, that's the same thing as saying adjacent over hypotenuse. So negative 1 over the square root of 10. Tangent is y over x, so that would be negative 3 over negative 1, or just 3. We can rationalize these, multiply by square root of 10 on top and bottom. So that would make that square root of 10 negative over just 10. This one would be negative 3 times the square root of 10 over just 10. If we want our other trig functions, because they did say just find all the values, remember that sine has a reciprocal partnership with cosecant. So cosecant of this theta would be, I would just flip it before you rationalize, that would be square root of 10 over negative 3, or put the negative out front. And secant theta is the opposite of cosine. So that would just be negative square root of 10. And the last one would be cotangent. This is positive 3, so the reciprocal of that is 1/3. So essentially, even though we've defined this with x, y, and r, it's the same idea of opposite over adjacent, or opposite over hypotenuse, or adjacent over hypotenuse. You're just really looking at why would we need this, and the example we'll start class on Monday with, you'll see why it's more relevant to use x, y, and r. It becomes the fact that you can't always draw a triangle, especially if you're looking at an angle that is pretty much just on one of the axes, like 90 degrees, 180, or 270, or 360. So it becomes more useful to think of x, y, and r in those cases. Hopefully this was helpful. I'm sure you'll have some questions, so we'll have some question time at the beginning of class on Monday, and like I said, we'll do a couple more examples to drive this home.